there's a guy at OS Dev. He says it's an interpreter. Okay, so repeat after me. This is a real this is a real mode bootloader. That you put this on the first block of your partition, and it uses interrupt 13 number 42. I wouldn't be surprised if Box is sabotaged. I wouldn't be surprised if Box is sabotaged. Interrupt 13, number 42. You pass it a DAP. Okay, that's just a packet with, you put 16.0, number of sectors, I put 1 segment, absolute. This is the address of your pointer. This is your block number. Okay, so interrupt 1342. I have okay. So I have here's my DAP. And you know what I do? I patch my DAP from my install script. A white man uses an install script. And right here I patch my DAP with the cluster number of my kernel.bin. The cluster number of my kernel.bin. And I store my kernel.bin contiguous. I patch it. So in other words, when this gets installed onto the partition, into the block, when this gets installed into the block, the first block of the partition, it is set with the block address of the kernel. It's set with the block address of the kernel. It's also set with the count of block count. You can see where I patched the block count, and here's where I patched the block count. So all it has to do is read 1 block at a time. I have it set for 1 block at a time, and every time it goes through. CX is stored with the block count. It has the block count. It pops it. It loops. So it's going to loop, and each time it goes through the loop, it adds the ES segment register is the destination. It adds a block divided by, so 512 divided by 16. It adds to the buffer position, and it loops. It adds with carry. It increments 1 block. so that loops through, calling one block at a time, interrupt 42, loading in all the blocks, and then when it's all done, it jumps to the base address. And do you know where that goes? That goes into my kernel, the kernel start, and it jumps down to here, skips over my data area, and here I set my I set up my stack segment. I put OS into VGA memory. I push, I do a call and then pop the stack, and that gives me my, this is position independent. I use these calculations to calculate what the CS, I get the CS and I add it and I figure out the address. I figure out the address that I'm running. This code figures out its own self address, and it puts the CS into the DS. Actually, that's after it normalizes the CS, I do believe. And now we can start using, since the data segment's set up, we can start using data. Now all of my 16-bit code is in the first 64 bytes of the file. So all these variables are tiny model. They're all in the lowest 64K. I call the interrupt, we're in real mode, I call interrupt 10 to enable VGA. Then I call the interrupt 15 to get the memory and get the E820 memory. There's the E820, 15 E820. I search for the PCI buses. I get that. I set enable A20. I don't do a complicated A20. I do a simple one. And then down here, we store the base address. This is 7C00. I calculate it with in real mode. You can use 32-bit values if you escape them. Trust me, I'm an expert on assembly. I wrote an assembler. You can use 32-bit values in 16-bit mode if you put a 66 in front of them. And down here we're storing, remember I said it's position independent. That means I have to adjust my GDT. My global descriptor table has to be dynamic. In other words, it's not a static value. My global descriptor table has the address of the data segment, or the address of the data segment. It's storing it, and then here's where I'm loading my GDT, and then here's where I'm loading my CR0. I give it an initial value that's fixed. I don't set a bit. And then in order to jump into 32-bit mode, I do the 66. This is I don't support segmentation in my assembler, so I have to do it by hand. These are DDs, you know, DD. These are DB and DD, except it's DU8, DU32. I assert this will generate an error if it's if we have exceeded 64K. It'll generate an error because this all has to fit in the first 64K. And at this point we are jumping to 32-bit mode. So all these this is a block of global variables, we jump into 32-bit mode. Now, if we're rebooting fast, if we're doing a fast reboot, then we don't jump into this. If we're rebooting, it loads a new kernel and then jumps into the to this position. We don't return to real mode. So now we're giving initial values to all the segment registers. And by the way, my GDT is set up for 64-bit. Notice my GDT is extra big, 6400. So that means there's a 0 entry. Every other entry is a 0 entry. I wouldn't be surprised if Box cannot handle 0 GDT entries. I wouldn't be surprised if Box has never been debugged for 64-bit. I am certainly not interested in debugging Box, okay? I don't give a fuck. Just use the goddamn VMware QEMU VirtualBox. You gotta be a stubborn fuck for 10 fucking years, fucking nigger. Anyway, so my code is position independent, and that's because I have a table of absolute addresses that I patch. So in other words, it's not position independent until I add the base address of the module to all the absolute addresses. And I give an initial, I initialize the floating point unit, and I save. This is a 512 byte save operation. It does the MMX SSE stuff. MMX. Anyway, so I save. That's once I save the initial state, then every time I make a new task, I want it to start with the initial state. So my task record has to start with it initialized. So now we start initializing the CPU record. The GS segment register is set to the current CPU. Now down here we start initializing heaps. Oh, where did we initialize the page tables? Well, we're getting there. Initialize memory, I guess there. Okay, so we're initializing the heap and stuff. I think we had to initialize the, we had to set up the page tables, didn't we? Of course we had to. That was for long mode. Where did we jump to long mode? Shit. Oh, there's where we jumped to long mode. Right here is where we jumped to long mode. Down here at the bottom is where we jump to long mode. We initialize CR3 is the page table register, and this EFR and LME. This is for it's write model specific. This is for changing to 64-bit mode. We have to set enable paging, and we have to we load the 64-bit segment registers. Anyway, up here, before we did all this, we had to set up the page tables. Where did I do that? Init sys memory. You know, I should say set up page tables. Why don't I call that sys init mem? You know what we're going to call that? Let's see, sys find PCI sys init page tables. That's what we're going to call it. It's a little bit more than it does a couple of block pools. So we say rename sys init mem sys init page tables. We identity map. That means we set 1-to-1 all the memory. We do 128 gig. So you know what that means? That means that mlBIOS, since we identity map, that means that the physical memory is the same as the virtual. Okay, so physical memory is the same as the virtual. So just to give you a clue, when you initialize the multi-core, it starts in real mode, and you have to step through. And I use the same GDT for all of them, and we eventually start calling. I use the same page tables. We call an initial. Why don't I call that jump to long mode? sys emt64t. That's okay. Nobody knows what that means except me. Okay. So somebody says emulating 64-bit mode. Okay, so ASM here. Let's go move RAX, comma, hello, call, put chars, return. Okay, call here, F5, pow, hello. So this is probably not going to convince you. Okay, hello. So I'm loading 1, 2, 3, 4, 5, 6, about 6 characters in. If we look up put chars, this is a 64-bit value, and we shift it over 8 at a time, and we print out the 1 8-bit character. So we shift all the. So we print characters up to 8 characters. So this is proof that it's 64-bit mode right here, because I used the RAX. That's proof it's 64-bit mode. What else do you want? Do you want, I can count to move RCX, comma, 0x, 2, 1, 2, 3, 4, 1, 2, 3, 4, add at 1. Oh, this is gonna peg it. We don't want to do that. Move U64 sys progress 1, comma, RCX, and loop at 1. Okay, let's do this from another core. Spawn. Okay, so spawn here 0, comma. Let's do bigger than that. Let's do that huge. 5. Okay. Spawn here 0, name or job. How about job? Comma, core number 2. Okay. Are you ready? Watch progress 1. Ready? Here we go. Pow. No. Oh, what? What did you say? No local global export. Oh, okay. What about that? No local global export. What does that mean? Let's see. Let's import that puppy. That's the quickest way. Import sys progress 1. No local global export. Oh, I did global export right there. Okay, never mind. Ready? Here we go. Pow. Okay, Control B. Control B. Control B. See that? Look at that. That's a 64-bit value. And we are, you don't doubt that that's the code, do you? Of course that's the code. So we're decreasing, we're counting down, and it's a 64-bit value using another core. It's going to go to 0, and then we're going to be done. There, it's done. Why is it 1? Oh, I don't know. Because. Anyway. So, it is, what about the stack? Do you want to see what happens when we push the stack? Watch this. How about this for proof? You want proof that it's 64-bit mode? In 64-bit mode, the stack is always 64-bit aligned. Call put hex use 64 return. Move rex carriage return. Call put chars. Okay, so we printed out the stack. Now let's push. Okay, so we printed out the stack. It's identical. Now let's say push rex pop rex. The stack has 8 subtracted from it. So that's proof that it's 64-bit mode. Okay, I proved it plenty. Maybe you want to see the machine code. You think it's an emulator? You're fucking nuts. He thinks I am emulating 64-bit mode or some shit. He's just. Why are you so stubborn? You're just a what do you call it? A troll. Fucking. Okay. So now I have to I changed a couple values. Page tables in long mode. I'm just recompiling. I'm rebuilding my website and everything because my website has all the code on it.